Hello, my name is Jacob Coleman, and in this video I'm going to show you how to make a simple spot diagram using COMSOL. So you can see here, this is kind of what we're going to end up with at the end. So the first thing that I'm going to do is use the model wizard in 3D, and for the physics module I'm going to use geometrical optics, and then I want to study ray tracing. The first thing that we're going to do is load in some geometry using predefined geometry from the part library. In the ray optics module under 3D, we're going to select and use a spherical lens and add that to the geometry, but it's going to ask us which variant. I'm going to use the specify clear aperture diameter. For the lens that I'm using, my first radius is going to be 60 millimeters. And the second, we're using a convex lens, so it's going to be positive and then negative. It's going to be 60 millimeters for the first radius and negative 353 for the second. And the center thickness I'm going to have as 4, and then the diameter of the lens I'm going to have as 25 millimeters. And I'm going to select all of these to be 25 millimeters. So then we can build it, and you can see then that the lens is, in fact, convex, even though there's just a tiny radius of curvature on that side. So then we'll define the material by browsing the library. I'm going to use NBK7. I think we need to specify, I'm searching wrong, it's actually like this, yep. And we will add this to the component. However, a weird thing with using BK7 is that it actually, oops, sorry, this didn't add, let's try that again. BK7, add this to the component. A weird kind of thing that we need to do when we're using this material in specific, and some other materials as well. We actually need to define the wavelength, which is the frequency, and we will define it to be 58 nanometers. And basically this will tell this material basically what wavelength it is, so then this knows what index of refraction basically value that it'll use. So it basically is actually how it'll work. So then for the ray properties, we can also select this to be 588. As well as under the geometrical properties module, we need to specify the maximum net number of secondary rays to be 0, because we're not studying stray light. We don't want any reflections. The next thing that we want to do is we want to send some light into our lens to see how it's going to act. We'll do that by right-clicking on this, or through a different menu. You might be able to find it, but we're looking for the release from grid. Then we'll pull up this menu, and we want to send in hexapolar grid of the grid type. Center location, we can have it be negative 0.004, basically right below where it goes into the lens. The cylindrical axis direction, we want to be in the Z direction, because that's the optical axis of our lens. The radius we're going to set to be 8 millimeters, or 16 will be the diameter. The number of radial positions will be 10, because that will show more points on our spot diagram, because we want to have a pretty good spot diagram. For the ray direction vector, we can set to be the Z direction. Alright, and then we can mesh it if we want. COMSOL can do that for us, but we can also do it manually. Under study, the first step, ray tracing, we actually want to specify a maximum path length, because I find that to be easier than specifying time. Let's let it go for 80 millimeters. That should be enough space to see where the rays come to a focus, because we're sending in collimated light, and then we will get out focused light by the lens. So now we can go ahead and compute it and see what result we end up with. All right, so this is what we get. Yep, and here's where our rays come to a focus. But if we zoom in, you can see it's actually quite a big diameter here, so it's not a perfect focus. What's happening is the lens is introducing spherical aberrations because we have a spherical lens, right? And we can get a better picture of how big that diameter is by using a spot diagram. So to get the spot diagram, we can do it multiple ways, but the easiest way is to right click on results, make a 2D plot group, and then under 2D plot group, we'll right click that as well, and under more plots, we select spot diagram, and it's right here. And then once we have our spot diagram, we don't actually know basically where the plane is that we want to find the basically what the light is at that plane, right? So we're looking for a focal plane, but COMSOL can actually compute it for us. So under focal plane orientation, if we click create focal plane dataset, it will automatically create this image surface, and it finds where the focal plane is. So this is the spot diagram at the most focused point of light, right? And you can see it's the RMS radius is pretty large, so there's a lot of spherical aberration going on. Another interesting thing, though, that we can do is instead of sending in light basically on the optical axis, we can send in light from a different place, because we oftentimes want to see, right, what's happening over here instead of just what's happening on axis, right? So we're gonna send in some light from off axis. To do that, we'll go back under release from grid, and under ray expression vector, we can select X or Y. We'll basically send in some light at an angle, and I'm gonna send it in at 4 degrees. So you can see I'm sending in tangent of 4 degrees here, and then COMSOL will know how to compute that basically. So then we compute it again, and then we'll get the ray trajectories. But then on the spot diagram also, we will need to. Here it is. So you can see it's no longer on axis; it's off axis, and you can see the light is coming to somewhat of a focus there. And then under spot diagram, it gives us this weird looking plot, and you can see this kind of aberration. We call this coma because it kind of looks like the tail of a comet. Fun fact, the word coma comes from a Greek word which means hair of the head. It's kind of fun, but actually this isn't the most focused spot because COMSOL left this image surface as from the previous computation that we did. So in order to change that, we'll go back under focal plane orientation and recompute the focal plane data set. And so now we get a different RMS radius. And you can see here's what our focused light looks like. It's very weird looking where there's this kind of tail here, right? It's actually pretty large. So, so again, going under the ray trajectories, you can see light is coming in off axis, and then it's kind of coming to a focus, and then it's dispersing. So this is how you make a simple spot diagram using COMSOL. I hope you learned something.